Welcome back to Unmanned Systems Engineering. So you've probably noticed that drones look wildly different from each other, right? Some look like tiny airplanes, others look like strange flying crosses, and some, well, they look kind of weird. But here's the thing, none of that is random. Every single design choice comes down to physics and engineering trade-offs. Today, we're going to be doing a deep dive on the different types of drones from a pure mechanics and design perspective. By the end of this video, you're going to understand why a racing drone can't survey a farm and why a fixed-wing drone can't hover over your backyard. Let's get into it. Before we talk about specific drone types, we need to understand something fundamental. There are really only two ways to get something heavy into the air. The first way is through aerodynamic lift. This is what airplanes do. The shape of the wing moving through the air creates pressure differences. Lower pressure on top, higher pressure on bottom. That difference pushes the plane up. The faster you go, the more lift you generate. The second way is through pure thrust. You point a propeller downward, it spins, and the air it pushes down creates an equal and opposite reaction, pushing the drone up. No forward motion needed. Every single drone type we're going to talk about makes a fundamental choice between these three approaches. And once you understand that choice, everything else makes sense. Let's start with fixed-wing drones. These are probably what you picture when you think drone that looks like an airplane, because it basically is one. It's got wings, it's got a fuselage, it's got tail surfaces for stability and control. Here's the core mechanic behind it. A fixed-wing drone must have forward motion to stay in the air. You can't just hover. The wings need airflow to generate lift. So there's a motor pushing it forward, the wings generate lift, and boom, it flies. Now why would anyone design a drone this way when we have quadcopters that can hover? Because of efficiency. When your wings are doing the work of holding you up, you're not constantly fighting gravity with motor thrust. You can glide, you can cruise. This means you can stay in the air for hours. We're talking 60 to 90 minutes, even more so for some professional models. Compare that to a quadcopter, 20 to 40 minutes tops. And that means range. A fixed wing can cover massive distances. We're talking surveying entire agricultural fields, monitoring infrastructure across miles of pipeline, search and rescue across forests. One flight can cover territory that would take a quadcopter dozens of flights. The payload capacity is similarly insane. Fixed-wing drones can carry specialized equipment, LiDAR sensors, thermal cameras, and multispectral imaging systems. Heavy stuff. Because the wings are doing the lifting work, the motors don't need to be as powerful. But, and this is a big but, there are trade-offs. You absolutely cannot hover. You need space to take off. Most wings need a runway or a catapult launcher. You can't just fly it from your backyard. They're less maneuverable because they're built for stable, forward flight, not agility. And they're expensive. We're talking thousands of dollars, tens of thousands of dollars for quality models. So when would you use this? Professional surveying, agricultural monitoring, environmental research, search and rescue over large areas, basically anything where you need to cover a lot of ground efficiently. Next, let's talk about quadcopters. 4 rotors arranged in an X pattern. 2 spin clockwise, 2 spin counterclockwise. That's it. Simple. And somehow this simple design revolutionized the entire drone industry. Here's why. Differential thrust control. Imagine you're sitting in the control room of a quadcopter. Your flight controller is watching 4 things: throttle, pitch, roll, and yaw. Throttle is simple. You want to go up, spin all 4 motors faster at the same speed. Everything's balanced, so you go straight up. You want to go down, slow them all down together. The drone sinks. But pitch, that's where it gets clever. You want to move forward. the flight controller increases the speed of the two rear motors and decreases the speed of the two front motors. The drone tilts forward. The thrust vector isn't pointing straight down anymore. It's pointing down and forward. So you accelerate forward while still generating enough lift to stay airborne. Roll works the same way but sideways. Want to go left? Speed up the right motors, slow down the left motors. The drone tilts left. Instant sideways movement. And yaw, that's rotation. The two clockwise spinning rotors have more momentum than the counterclockwise one. That imbalance creates a twisting force, and the drone rotates. The beautiful part of this is that the flight controller is doing this constantly, hundreds of times per second. Your accelerometers and gyroscopes are feeding it data and is making tiny adjustments to each motor to keep everything balanced and responsive to your inputs. That's why flying a quadcopter feels so smooth and intuitive. Now, why do you use this design? Because you can hover. You can do this right now. Stand in your backyard, turn it on, and it just hovers. No runway needed, no forward motion required. You can fly in any direction, forward, backward, sideways. You can point the camera down, twist the drone's orientation without moving it, and then fly sideways while keeping the camera pointed at something. That's not possible with a fixed wing. Quadcopters are compact, portable, and they've gotten affordable. You can get a solid one for under $500. And the response is instantaneous. You want to dodge an obstacle? Move the stick and it reacts immediately. The trade-off, on the other hand, flight time is limited. You're fighting gravity the entire time. Those motors are working hard. Most consumer quadcopters run out of battery after 25 to 40 minutes, and they're not efficient in wind. A strong gust will push them around because they're relying on rotor thrust, not aerodynamic stability. Now, when would you use a quadcopter? Aerial photography, FPV racing, indoor inspection, real estate videography, any close-range work that requires agility and precision. This is the workhorse of the drone world. Now, what if we just add more rotors? That's the basic idea behind hexacopters and octocopters. More thrust, more redundancy, more stability. A hexacopter has 6 motors arranged in a hexagonal pattern. That means 3 pairs of counter-rotating motors. Same control principle as a quadcopter, but more power. You can generate more total thrust with the same size rotors, or use smaller rotors and generate the same thrust more efficiently. Here's the thing that's really important. Redundancy. If you lose one motor on a quadcopter, you're crashing. It's just physics. 3 motors can't maintain balance. But a hexacopter, lose one motor and you can still fly. It's not comfortable, but it's possible. That's why they're used for professional work where reliability matters. Octocopters take it further. 8 rotors, 4 pairs of counter-rotating motors. Lose 2 motors, still flyable. That's serious redundancy. And the payload capacity? Massive. Professional cinematographers use octocopters to carry crazy heavy camera rigs. Cinema cameras, gimbal stabilizers, wireless systems. We're talking 10 kilograms or more of payload. But notice the trade-off. More rotors mean more weight. More weight means you need bigger batteries to generate the same flight time. So while a quad might fly for 30 minutes, a hexacopter with the same battery might fly for 20 minutes and an octocopter for 15. You're also dealing with more complexity. More motors to control, more failure points, more cost. A professional octocopter isn't cheap. So when do you choose these? When you need serious payload capacity, when you need redundancy, when you're doing professional work where a crash is expensive. Cinema, heavy sensor work, industrial applications. Now here's an interesting question. What if you could combine a fixed wing's 90-minute range with a quadcopter's ability to take off from your backyard? That's the problem VTOL drones try to solve. VTOL stands for Vertical Takeoff and Landing, and there are a few ways to do this. The most common approach is what's called a quad plane. You've got a fixed-wing aircraft with 4 vertical lift motors attached. You take off vertically using those motors like a quadcopter. Then, as you accelerate forward, the fixed wing starts generating lift. You transition to horizontal fixed-wing flight, and those vertical motors basically turn off. They're just dead weight at that point. Then, when you want to land, you reverse the process. Slow down, the wing stops generating lift, switch back to the vertical motors, and land straight down. Another design is the tilt rotor. The rotors themselves can physically rotate from pointing down to pointing forward. It's more mechanically complex, but the transition is smoother. There's no moment where you switch control systems. The advantage, you get the best of both worlds. No runway needed, but 40 to 100 minutes of flight time, extended range. You can map large areas and still take off and land in confined spaces. The challenge of it? That transition is hard. You've got to switch from hover mode to forward flight mode mid-air. The flight controller is doing completely different math. Get it wrong and the drone stalls. It's why VTOL drones require more training to operate. They are more complex, more expensive. We're talking 15,000 to 50,000 for decent commercial models. And the transition isn't always smooth. But if you're doing professional surveying and you don't have a runway, this is probably your best bet. Search and rescue over difficult terrain, VTOL is ideal. Emergency response, we need both efficiency and precision. VTOL solves that problem. What if you removed the fuselage and tail? What if it was just wing? That's a flying wing. No fuselage, no tail, just wing. Pure aerodynamic efficiency. Theoretically, this is brilliant. Minimal drag, incredibly efficient. Military drones use flying wing designs for stealth because they have a small radar profile, and they can be incredibly fast. But here's the problem. They're inherently unstable. A normal plane uses the tail to provide stability. The tail prevents the plane from pitching up or down unexpectedly. A flying wing doesn't have that. So engineers have to use something called a reflex airfoil. The wing actually curves up at the trailing edge. That creates its own stabilizing force. But even with that, a flying wing needs constant active stabilization. The flight controller is always making micro adjustments. If the computers fail, it falls out of the sky. That's why you don't see flying wings in consumer drones. Too risky. They're mostly research drones, military applications, and experimental aircraft. They are proof that aerodynamic efficiency is possible, but for most applications they are overkill and too complex. There are other specialty designs too. Some drones have tilting wings, some have tilting rotors in different configurations. The point is, engineers are always experimenting with new ways to solve the fundamental problem. How do you get something in the air, keep it stable, and do useful work? For a moment, let's talk about what you should choose. So, you as the consumer, or you as a researcher, engineer, creator, how do you choose? Which drone works best for you? Need to hover? Choose a multi-rotor, a quad, hex, or octo. Need long range and efficiency? Look for a fixed wing or VTOL. Need to be stable in wind? More rotors or a fixed wing. The more aerodynamic surfaces, the more stable you are. Need agility? Quadcopter. Need a heavy payload? Fixed wing or octocopter. Every drone type is engineering built for a specific job. Understanding why they are different helps you pick the right tool. Thanks for watching. If you're interested in drone tech, stick around. And when you're thinking about building your own drone, understanding these mechanics is where you start. Hit the like and subscribe if you're interested in more drones. See you next time.